Welcome back, everybody. This is our video solution to problems 3 and 4 from Quiz 11. This is Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. And in the first problem, we are simply asked to state the complex spectral theorem. Problem 4, we'll get to apply it. So here we go. Problem 3. We're going to state it. So we're going to start with a complex inner product space V. Okay, so let V be a complex, and of course everything is finite dimensional for us, complex inner product space. And then we need an operator on V. So we'll call that T. Okay, so the complex spectral theorem is going to create three equivalent statements, right? That's what we're going to be getting to. So the following are equivalent. And the first is that T is normal. Okay, so T star is equal to T star T. All right, the second statement is that V has an orthonormal basis of eigenvectors. Or if you like, it's an orthonormal eigenbasis. That's probably a nice, faster way to say it. An orthonormal eigenbasis for T. Okay, of course, the 4T is referring to the eigenbasis part. The orthonormal has to do with it being an inner product space. And then finally, this means that T is diagonalizable with respect to an orthonormal basis. And of course, again, once you know that it's diagonalizable, that already tells you you must have an eigenbasis. So, but with respect to an eigenbasis of V. Okay, so that is what the complex spectral theorem is saying. Complex spectral theorem. Of course, there's a real version of that out there, but in that case, you need your operator to be self-adjoint and not just normal. All right, so let's move on to problem 4. Problem 4, okay, look, it gives us an inner product space over the complex numbers, right? That's a complex inner product space. But here, we have three linear operators. Ooh, not just one. D, U, and T. Such that, okay, so there's three conditions. First one, with respect to an orthonormal basis, okay, the matrix of D is diagonal. Oh, well, let's go back to our complex spectral theorem. If we know we have a matrix which is diagonal, then that means that our operator is diagonalizable. And let's see, with respect to an orthonormal basis, and hey, look at that, with respect to an orthonormal basis. So this already, by the complex spectral theorem, complex spectral theorem tells us that D is normal. All right, so we know that D star is equal to D star D. Okay, what do we have next? This matrix, or rather this operator U, has the property that its adjoint is equal to its inverse. All right, so this is called a unitary operator. And then finally, this T is given by, well, you take the diagonal matrix D, and on one side you put U, and on the other side you put its adjoint, or if you prefer, its inverse. Okay, there's actually something that's called conjugating D. All right, and so this actually gives you what's sometimes referred to as a similar, well, if we were talking about matrices, a similar matrix. Okay, so we might call T and D similar as operators. All right, so it now asks us to prove that V has an orthonormal basis consisting of eigenvectors for T. So we know already that it has an orthonormal basis consisting of eigenvectors for D. But now we want them for T. Okay, well, by the complex spectral theorem, in order to know that we have an orthonormal basis, right, of eigenvectors, so an orthonormal eigenbasis, it's enough to show that T is normal. All right, so for our proof, this is essentially saying by the complex spectral theorem, T is normal. Oh, okay. But to show that t is normal, right, that's equivalent to showing that t star is equal to t star t. Okay, well, let's head on down and try that. So t star t. Well, let's see, what is our t? T is given by u star du. So this is going to be u star du star. And then we have the t, so that'll be now u star du. Okay, well, let's see. The first bit, we take the adjoint of a composition. You take the composition of the adjoints, but in reverse order. So this becomes u star d star u star star. And of course, u star star is just u. Okay, and then the second bit, well, that just remains u star du. Okay, well, now let's take a peek here. I notice I have u and u star adjacent to each other, and u star is equal to u inverse. Oh, u inverse is the identity. That's just going to go away. So I'm going to get u star d, and then a u, right? These middle u and u star or u and u inverse go away. But now I know that d is normal. So d star, and d star d are the same, so I can take this d star d and rewrite it as d star. Ah, now I can play this game. I'm going to stick the u's back in. So I put u star d, and now I'll put the u inverse inside. That doesn't change anything. D star u. Okay, well, again, this u inverse is the same as u star. And now I can just break this up. This is u star du. And then the other bit is, well, I have u star d star u, but I could pull a star out. And if I pull a star out, it becomes u d u star star. Oh, wait, that can't be right. I didn't switch the order, right? Okay, so this becomes the star, and that becomes it, right? So if you put this back in, right, this star here, you'd get u star star, which is u, which goes on the right end. You have d star, which goes in the middle, and then you have u star, which goes at the front. Okay, but this first bit, that is exactly what t is, and the second bit is exactly t star. And so we've shown that t star t is equal to t star, and therefore t is normal, and therefore v has an orthonormal eigenbasis for t. And there we go. We've done the problem. All right, everybody. We'll see you next time.